Actually, I have a question. So maybe we could talk. Let me.
Okay.
Yeah, please.
Yes, I would like, for the formula definition, um, it seems to be clear, more or less. I think it the first explanation is not so difficult, but I am trying to understand where are required the the constraints of being small or locally small. So
Hmm. I don't know much about that, the foundational things. You're asking like, why are they not sets, or
is the question, what is the difference between small and locally small?
yes,
What is local about the smallness?
yes.
Oh, I see.
Yeah, so locally refers to hom sets. So if you have any two objects in a category, you can consider the class of all morphisms between those two objects. Yeah. In general, this will be a proper class. But if it's a reasonably manageable category, that thing will be a set. If it is, for example, if you're in the category of groups or sets themselves, then they're given by mappings, and there's only like a set many of them, not a huge number. Although the category of sets is locally small for that reason, but the category of sets is not small because the collection of all sets is bigger than a set. Does that make sense?
Yes.
But it is a good question because it's in the assumptions for the proof, right? But I don't remember them explicitly using it in the proof. It must be used somewhere implicitly. If you're talking about the first result, which they proved in section 6.2.
Yes, I don't know where these assumptions are used. And I was asking myself what happens if these assumptions are not reached. Is it still possible to have something or not? Or where the
related to co-limits? I mean, can you have co-limits in things that aren't, where the hom sets aren't sets? I don't know. It may be implicit in something that, if we went back and read all the details, it's like, oh, this has to be, these have to be sets.
So I'm looking at her treatment briefly of limits and co-limits, and I don't see any set theoretic restrictions there.
Okay.
But it's interesting. So at the top of section 6.2, she says, we will see that these exist along any functor, left and right conextensions exist along any functor whose domain is small and whose codomain is locally small, whenever the target category has certain limits or co-limits. But then in the statement of theorem 6.2.1 on the next page, there is no assumption of small or locally small. Is that true? I think that's true.
At the beginning of 6.1, she's talking about conextensions in general and says it could be stated for two categories other than the two categories, functors and natural transformations.
Mhm.
So I guess, maybe there's ways of like reformulating this in these other two categories where things maybe aren't sets. Does that make sense?
Sorry, say it again.
Well, just at the beginning of 6.1, she mentions that the con extensions that she's defining it, I guess, in the two category of where you have the category of categories or category of sets and things like that. Where'd it go?
Yeah, you want to share?
Two categories other than the two category of categories, functors, and natural transformations.
Yeah, so you can define this more generally in any two category, just as the way you can define adjoint junctions in any two category if you want.
Okay.
But here, I guess we're restricted. There is let me share my screen if I can. Context. Is that working?
Yep.
So we're in here, yes. So at the beginning, we were talking about the formula. She says left and right con extensions exist with these assumptions of smallness, right? So then, but we get into the theorem. D. So this doesn't actually appear to assume anything in particular about these categories. But there is one thing. I did see a mention of sets somewhere in there. Oh, right. Okay. Well, this is somewhat relevant in here. And actually, this puzzled me. So this part here, when she says, so there is this comma category, K down arrow D, which is the category of morphisms from images of objects in C to the object D. And she says it's equivalent to this thing, the category of elements. And I did not realize, I just sort of breezed past this statement at one point and said, okay, whatever, I don't need to know that. But I realized today that category of elements is a specific technical term. She's not just talking about like elements, which are elements of the class of objects of a category or something like that. Category of elements is a thing.
That she defines,
It's defined up above. And let's see, it has to do with representations. Yeah. See over here.
Page 66. Yeah.
Yeah.
The-
And that's why in the con extension thing, we've been seeing these integral signs, which is confusing because integral signs also mean ends and coends. And these are not coends. This is a totally different thing, I believe. Anyway, if you have a functor to the category of sets, then you can take a derived category from it, which is pairs, the objects in C and an object in C together with an element of its image. Then a morphism between the objects in C has to be compatible with that extra structure. The element that you've chosen here has to map appropriately when you take the image in sets. Anyway, so that's something to know about when you're reading about those things. And this obviously is a set-related thing, but and by the way, this is a digression. But last time we talked about the first two exercises of section 6.1, which I did. I worked on exercise number 3, but I didn't get very far. And I think the reason is that the key concept that's missing here is the category of elements, which I didn't know because we we parachuted into section 6, right, without reading the rest of the book.
Mhm.
And anyway, you can look into that further if you want.
So wait, you're saying that part of the solution is to use the category of elements?
In here, yeah, she says, explain the connection between this category and the functor. And I think you have to take the category of elements of that functor and you get the appropriate category for defining right Kohn extensions, I believe. Anyway, that is a side note, and we still have Antonio's question. So this is, but okay, so that's specifically about sets. Yeah, I don't see anything. Honestly, I only made it through the first 1 or 2 pages of this, right? So it could be that it comes in later in the section.
I drew some pictures relative to this.
Cool. Yes. No, more
thing.
pictures. More pictures do help. I drew a few myself.
Oh, you want to go through them?
Oh, I don't know how helpful they would be. Yeah, maybe. But let me actually just look through this and see if I can find like a hidden use of some sort of small condition.
Local.
Yeah. But it's more than that, right? C is, sorry, what is it? Yeah, C is supposed to be small, in fact, and D is locally small. That's what she's saying. But in here, okay, so colimits can exist anywhere. You don't need any smallness assumptions on that.
And it's not about C anyway, it's about D, right? Oh, wait, yeah, D. Right. Where'd that go? Because K goes from, oh, I see. Wait, okay, yeah.
K goes
I
from
was
C to D.
misspeaking. It doesn't say anything about E, and that's where we're building our colimits and stuff like that. So it's really saying that C is small and D is locally small.
That's true. That's true.
And we're not doing that much with D other than building the comma category sort of from it.
Yep. Which is, I think that makes complete sense, you know, regardless of smallness. Cone, those are the cone. I guess smallness gets relevant if we do something like use Yoneda, right? Because in Yoneda, I think Yoneda really only works when the category is locally small, because you're talking specifically about functors to set.
Just looking at the, maybe in support of that, just looking at the diagram, because you have composition, and I think maybe you have like composition, it's kind of related like to Yoneda lemma. So for composition, maybe that's why the locally small is important, because you're composing in through D, which is the locally small.
So the diagram like this one?
Yes.
You
So
can see
like
my
C
cartoon.
is small, but D is locally small, means that each Hom set is a set. So and so just intuitively, because we're composing through D, right? That would be the reason for that being more strict than for C. That's just a guess. Because locally small is more strict than small, right?
Actually, no.
No?
Yeah, because locally small applies only to the Hom
Oh,
classes,
I see.
right? If C is small, then it is in particular locally small, because like everything in it fits into a set.
That's my error. That's right. You make sense.
Everything, yeah. So on the other hand, if we're taking limits and colimits, so we're thinking of C as being kind of like a diagram schema, then it sort of makes sense that it should be small. But Yeah.
I mean, C does factor into the diagram, sort of, yeah. Because basically the diagram is images of C, you know, through F.
Yes.
It's not all of C, because it actually has to come from K down arrow D, but it kind of goes through C to get there.
Yep. Unique morphism. I had a little trouble with this diagram, but we can later.
Yeah, I did not
Okay.
get to that.
So we need to show the universal property. Okay. I didn't get here either. Unique factorization. Composite. I don't know. This looks like general abstract nonsense to me. I don't see any use of smallness in this proof. Oh, maybe it's only here. Maybe it's this
Yeah,
part
this,
he's really interested in.
yeah, smallness. I think in the theorem, smallness is not necessary because the theorem is talking about if the co-limits and limits exist, right? But then in the corollary, if C is small and D is locally small, then they will exist. I think that's the conclusion, right?
Well, but there's also an assumption of co-completeness on E in here.
Right.
So I don't.
But then in the proof, right?
Yes, right. And here the comma categories are small. Oh, so the respective. Oh, okay. So there are theorems about completeness and co-completeness which require smallness. Yes. Okay, I see what you're saying now.
I think, unless I'm misreading that.
No,
Because
I
the
think you're right.
completeness and co-completeness is on E, that is true. But
But what we want to say also is that we want to say not only that E is co-complete here, but that other categories derived, like functor categories involving E, things like that, should also
Well,
be co-complete. And then we can.
in the proof of that corollary, it mentions directly that it's because of, like, if C is small and D is locally small, then for
Yeah.
any D element of D, the comma categories, D, I don't know how to say that, D down K and K down D are small. So the respective completeness and co-completeness hypotheses ensure that the limits and co-limits of theorem 6.2.1 exist in E. So those.
Huh. So somewhere she explains that, I guess, the co-completeness, the completeness and co-completeness.
So what?
Am I right? Like completeness means that all limits exist, and co-completeness means all co-limits exist.
yes.
But maybe it might be that there are restrictions that there are smallness restrictions on that. Let me actually see limits and co-limits. Where does she define complete? Where are her basic theorems on completeness and so on? Oh, completeness. Okay.
3.5. Okay, you got there.
Okay. Complete has all small limits or co-limits. Okay. So yeah. So I guess limits get awkward if your domain category is not small. So her definition of co-complete in this case means that all small co-limits exist. That is, whenever you have a functor into your category from a small category, that functor has a co-limit. Does that sound right?
Say it again.
Yeah. So co-complete, in our definition of co-complete, basically co-complete means that all co-limits exist, right? That's what Anvius was saying. Did I say your name right? Just as the definition of complete is that all limits exist, right? So they're dual. But in her definition, she also requires that the limits and co-limits must be small. Those are specified. So what does that mean? Small co-limits. Okay, so definition of limits and colimits. So you can take the limit, you can ask whether the limit or colimit of a functor exists, right? That's what it means. You regard the functor as a diagram. It's just a functor from categories, any category J to C here, but you regard it as a diagram of objects and morphisms in C whose shape is taken from J, just like that's the intuition behind it. So in order for this to be a small situation, you need your, I think you need your source category to be small.
Usually these J's are like finite, or are they countable? Like they're
Exactly.
they're tiny.
Yeah,
Is that right?
yeah. So like if like one of the first examples of a limit is the product, right? Product of two things, in which case your J is the discrete category, which has two objects and no non-trivial morphisms.
So do these shapes have to be finite, or can they be countable?
No, they don't have to be finite. They can be infinite, countable, uncountable, whatever, as long as they're small.
Okay, but they have to be small. They have to be
They have to be
sets.
small.
Ok-
So it could be, the
Or-
size of the real numbers or something like that.
Okay.
But it has to be something you can describe as a set, apparently. Now, I don't know why she puts that condition on, but it does, that does kind of make sense now, where the smallness is coming from, where the smallest assumption is coming from.
The diagrams that we're creating for this, this proof, they're not
Yeah.
finite because they're coming from C, and C can be arbitrary. So
C is more or less arbitrary, but pretty soon we're going to want C to be small.
yeah.
So it's not arbitrary, it's not the category of sets, for example.
Well, but yeah, right. But I'm saying it's not finite.
It's not finite.
So when we project into E through F and stuff, it's likely that the diagram's going to have an infinite number of nodes.
Yep.
Okay, but so could we repeat what had to do to the smallness to be complete and co-complete? Because
Yes.
we could have limit and co-limits even for a not a small category.
Yep, absolutely. So as far as theorem 621 goes, there are no smallness assumptions. I think, if you got that far, if like me, you only got that far and you didn't see any smallness, that was correct.
Yes.
It's not there. So where it shows up is here.
Corollary.
Here.
Not even being locally small, right? All these things we were saying about the Yoneda lemma, and the requirement to be locally small for applying Yoneda lemma, it's not applying here. It's not necessary.
That's right. That's right. Sorry, I was just babbling. I was just speculating about why it might come in, but yes. So yeah, right up all the way up to here, we're not actually using any assumption of smallness. We're pretty sure it comes in right here. So we think that the reason for this exact requirement is so that these comma categories will be small. Is it clear why you want D to be locally small?
Well, the comma category is built on the Hom sets in D. It has objects of C, and then things from the Hom
Right.
set of
Yes.
KC to D.
Right.
So
That's exactly right. So what is an object of K down D? It is an object of K together with sorry, not K.
it's an object of C.
An object of C together with a morphism in D.
Right.
Right?
From
Right.
KC to
And the
D. Right.
and the morphism of
Right.
morphism in D has to be from that particular Hom set. Okay, so if C is small and D is locally small, then we know that the collection of objects here is small, and the collection
Small.
of relevant morphisms over here is also small. So that means this whole thing is small. Okay, that kind of makes sense. But now, okay, she's doing this to make sure that the limits and colimits of theorem 621 exist in E. Okay, so why is she doing that? So specifically, I just did the, do not do that, please. Go page. Page, continuous. Okay, sorry about that. Okay, so she wants to get this assumption. She wants this to be true. She wants this colimit always to exist.
Right.
And she's trying to do that by making sure that this thing here is small. So is it true that any functor out of a small category has a colimit? That doesn't sound right.
E is co-complete. I think that's what she says, and then that will make your assumption
Right.
of 6.2.1 hold,
co-complete,
and then you
yes.
can apply the theorem.
Yes, thank you. Okay. So E is, all right, so E is co-complete. What does co-complete mean? It means that any diagram, any small diagram has a colimit. Right. How do we know that our diagrams are small? Well, because we've made sure that K down D is small here, and that's the source of our functor. It's the shape of the diagram is coming from.
It's the shape,
K down.
yeah.
Okay. Does that make sense, Antonio?
Yes, yes. Now this was very helpful. I was just lost about the the entire procedure, but you have organized my view. So thank you
Good.
for the explanation. Yes, I just read the beginning, and actually I didn't reach this corollary, and I didn't read also the the definition of being complete and co-complete. I was thinking that, okay, where are these assumption or this requirement of being small and locally small be used, right? Now I have a much more clear.
Cool. Yes, no, waning is right. It shows up right here. The co-complete thing. Presumably, then we have lots of examples of categories which are complete and co-complete. Probably like the category of sets, for example. And
So
I
are
still-
you saying that part of co-completeness is that the colimits exist only for small diagrams?
Yes, exactly.
Okay, okay.
And I guess, yeah, I guess that kind of makes sense. So we previously have gone through or sketched rather proofs that the category of sets is complete and co-complete. And the way you do that is, you get a diagram and then you construct something which is supposed to be a limit or co-limit, right? But how do you do that construction? Well, you might need things to be sets to do it, right? You have sets and you can build other sets from them. So it kind of makes sense that the diagram shape must be small. Cool.
Question. So I don't understand in which way this might be a general rule. I would understand is that if I examine a certain question with a limited range of source, so I can derive something from it because I know my objects. But I don't understand in which way that should be a general rule, because in this case, it would depend from the precise character of the objects I have to deal with as source to see what will happen, what I can derive from it. But I don't understand it in this general setting as category.
So wait, so what statement are you talking about? That seems
The idea of a locally small category with home set, and you just answered that question. But I don't understand. I understand that we can have some small or locally small as condition to derive rules or operations on it, but I don't understand in which way it should be a general idea here in category theory, because it would depend from the precise nature of the objects, what I have in this category. I don't understand the generalization of this idea. Just a comment. So you must not answer
Okay.
that.
okay.
So you're
It is
saying that you're looking for a generalization of this idea, but we're not sure what it is. Yeah, I don't.
Yes, I just don't understand the role it plays here in this theory, because
Oh.
I understand if something locally small, I can look at it, I can grasp it, I can derive rules from it, I can say something on it, but it's a matter of practice for me. But in theory, we are here in a very abstract thing. I cannot see how I can derive something from it when I don't know the precise things. Just say they are small, but I don't know more about it. So I don't know, I don't understand this deriving from that assumption.
I think, just personally, speaking mostly out of ignorance, but I think that this is all about whether or not we can use set theory. So usually we assume we can use set theory, just very basic things, that the set exists. But category theory is so broad that you can't always assume that. These and then these notions really are kind of dubiously founded in the first place. Like what is a set is not very well defined as far as I know. But we work with category of sets all the time. And so it's just a way of saying that it's workable with regard to set theory and precisely, what are the things that are being covered. But so that doesn't really answer the question, but that's maybe someone has a better intuitive understanding.
No, I think your intuition is right. I mean, yeah, we, as you say, we tend to assume that everything we talk about is a set intuitively, just so that we can think about it. But we know, that if you're not careful and you start saying things about classes, then you wind up with paradoxes, right? So at some point, to be precise, you want to lay down some guardrails to make sure that the things you're talking about, can actually be constructed and actually exist. And I think that's what these are.
Yeah,
And
I
don't
mean,
lead to paradoxes.
Yeah.
yeah, for example, when we talk about a category of categories, right? Is that an element of one of the, is the categories a category in that, and so on, right? So to me, category theory is in a way moving away from the constructions in set theory, the predicative nature and distinctions between set and class and things like that. But the way it maintains consistency could be an issue. But the way it resolves it, I think, is by always having the levels, right? So you have the level of object, and then you've got functors, and then you've got natural transformation. And so any structure that satisfies those three, you admit. So category of categories could have itself as an element, an object of that category of categories, right? But we're not defining things, like we're not doing like universal quantification and things like that, but we're more constructive in our approach. And I think that's how the contradictions are avoided, I believe.
And there's one very funky thing about category theory. For me, it took me a long time to realize, it still kind of makes me wonder. But in category theory, like when they talk about the category of sets, it includes many copies of basically the same thing. So like, you can have the set 1, 2, 3, you can have the set A, B, C, you can have the set cow, sheep, horse, and, or like, when you have the group, you can have all kinds of trivial groups. I think they're all, there's not like a unique trivial group. There's not a unique set with, singleton set. So the whole thing just becomes, and I think the reason for that is that when they do things like group homomorphisms and they get different versions of the same group, they want to be able to say that they exist in the category groups, let's say. But just as a mathematician, it's just very strange that you would not want to simplify things down and say, well, there's like one object of each kind, but that instead there's this bizarre infinity of objects of each kind. It's not clear what the size of that infinity actually is, as far as I know. So I just find that like a big non-clarity what's going on there.
Yeah.
Well, right. I mean, that's why the notion of equivalence class comes into the picture, right? Basically, any set of, say, equal number of is considered the same or equal, and then you deal with those. But what the issue that you're, I think, addressing is, in order to even come up with the notion of an equivalence class, in a sense, you're at a higher level, right? The relationship, the equivalence class relationship is very large. Is to say that anything that is 3-element is equal in set theory, you have to represent that as another set, right? Because relations are also sets. And so the equivalence class is represented as a set, but that's a huge set.
Yeah, it's not a set, actually. It's a proper class. So,
Okay. Like in mathematics, as practiced by people like me, I think you define what you're drawing from first of all. So like you'll start with a set, like you're starting with something you're constructing from, so you say the integers are a set, that I think I believe in, and then but see, I don't think that's the approach category theory takes. They're not drawing anything from anywhere. They're just allowing anything to be whatever it wants to be, you see. So it's very, so it's kind of constructive in terms of like what's a natural isomorphism, it's very constructive in terms of its operations, but it's completely non-constructive in terms of where these objects are coming from. And that's just very the opposite, I think, of how math usually works. So usual math, like you have to be very clear where your objects are coming from, but then you can do things like axiom of choice where you don't, you just say, well, there's a way to choose.
Right.
So category theory is kind of like opposite in style.
Mm-hmm.
But I think it's also true that you could ignore all of the set theory problems and just read this section, and you would still get the idea. It's like
right.
On
And so
a first pass, you can ignore these issues because you probably won't run into them, right? I mean, you probably are not going to accidentally generate a paradox just by messing around with this stuff. So
well, and so it's the whole issue of like, I mean, personally, that's exactly how I look at it. Just kind of like ignore these things. But then the whole project of like, is math consistent? Is math, for people who are sensitive to those issues, that's it just left aside. But I'm interested more in mathematical intuition, so I'm more not really caring about those things.
Right.
I agree.
Yeah. I mean, one historical note is the lambda calculus, for example, was considered inconsistent for a long time because of the self-application, right? Because the self-application in type 3 lambda calculus resembled, X is a member of X. But it turns out that there is a model, namely D infinity model, but that is not a set theoretic model. It's a continuous lattice theoretic model. And so by imposing a certain continuity structure to it, you could come up with a model, which then showed that the type 3 lambda calculus is consistent, is not a contradiction. And so by imposing an extra structure, continuity, which in my view, continuity is a mathematical notion of what is computable, right? If computable things are continuous, so.
All right, so say that again. So you're talking about like denotational semantics, the D
Yes.
infinity?
That's
Okay.
right. Exactly.
And continuity is what then?
In order to show in denotation semantics, for lambda calculus, you need to have a domain which is equivalent to the functions from that domain into itself,
Okay.
right? And in set
Yeah.
theory, the function space over a set into itself is always cardinality bigger than the set itself.
Mm.
Therefore, you cannot have an isomorphism between the two. But using continuous lattices, you can restrict the function space so that it has the same, you can have an isomorphism between D and D arrow D.
Hmm.
And Dana Scott constructed that. At first, he didn't think that lambda calculus, the way it was used at that point, was consistent. But then he came up with this model, and voila, now lambda calculus, the type-free lambda calculus is fine, right?
Hmm.
So there is this non-set theoretic, namely lattice theoretic model. And I think what category theory does is it allows those kind of other things that are not sets to be treated on an equal footing, at least.
Hmm.
So,
That's interesting.
and the notion of continuity is that if you have a limit of things, then that limit exists, right? And that's what we do with programming languages. Whenever we define a recursive function, you can think of it as, like the factorial function, you can think of it as, first thing is f of 1 is 0. I mean, f of 1 is 1. And then for every other number, it's undefined. And then you can say f of 2 is equal to f of 1 times something. And then for everything else, it's undefined. So you can have a hierarchy of functions that are bigger and bigger, defined on a larger and larger domain. And then the limit of that is your recursive function factorial, for example. And so if you can compute it, represent it in a computable way, then it's automatically continuous in that way, right? I mean, the notion of continuity, it captures the notion of computability there. And so.
I wanted to add just a piece of little intuition that regarding comma categories that I'm still trying to grok about, but where they have this D down K and K down D, really, I think with comma categories, let's see, yeah, I guess the D down K and the C, like it's actually helpful to think of there as being 3 categories. So like, let's say, you would be going from C to D and from B to D. And what the D category is doing, it's kind of relating objects in 2 different categories, I think. So like you could have a category C and you could have a category B, and normally they're separate. They don't have any way to look at the objects. But if you have this comma category, then you have a functor from C into D and a functor from B into D. And now you can imagine the objects of C and the objects of B as sitting inside D, and they can have relations inside D, morphisms. And I think that's what they call it. But in the particular comma category that they're showing, I don't know if it's called like a slice category, but it's a simpler version where one of the categories is just the unit category with just one element. And then, so when you have a map from there into an object in D, then it's kind of like the arrow from 1 to D. That's the limits of my understanding, but.
Right.
Yes.
It's like the constant functor into D.
But so sometimes
it's every element into D.
Usually they teach it by starting with the simpler quote unquote thing, the triangle or whatever, and then expanding out. But I think sometimes in this case, like the more general situation may be more helpful to figure out what's going on here than the more simpler quote, the more smaller situation.
Right.
Yeah, so when she says K down D, little d is she's abusing notation slightly here, because really the comma category, both of these things should be functors.
Right. That's the general.
Functor, down arrow functor, and little d is standing in for the functor, which
constant.
is from the terminal category to the category big D, whose value is the object little d. So yeah, that
Yeah.
is where that comes from.
And then you see if it was like KC goes to LB, capital LB, then the thing would be much more symmetric, and it would just kind of make more conceptual sense. Like, what are they doing? But when they, instead of capital LB, they just have this D, which is inside the category D. Then you're wondering, like, that's so asymmetric, and what could that possibly mean? So that's just a degenerate version of the more symmetric picture.
Yeah.
Right.
If you want to know more about comma categories, then you have to go back and look at the more general version. But in this
Yeah, I
case,
don't
in
know.
this case, they are pretty simple. I guess if you want to know that this is a category, for example, and what it's, that the morphisms actually work and stuff like that, then you might want to go and check that. But in this case, it's actually pretty simple to check that everything works.
Yeah. On page 22, she defines in exercise 1.3, she defines that comma category
You know what
using
section that is,
functors.
Sam?
Yes, it's section.
I want to be able to navigate back if I can.
1.3, section 1.3, functoriality, and then go down 1, 2, 3, 4, 5, 6, 7, 8, 9 pages to the exercise.
What's the page number?
22,
Oh,
page
you said
22.
that.
Yep, there you go, comma category. So yeah, that's the general definition, F down arrow G. So you're right.
And Wikipedia has, I think, a decent article about this, all with the different subcases. And
Mhm.
But it is also important that you have these projections, right?
Yes.
Which actually is pretty easy to see in the individual case. But if you had a comma category, so as Andreas was saying, it's, let's see. So these are two categories, in this case, D and E, which can be related because they both have a functor. You have a functor from both of them to C. But if you just want to project on, if you just want to forget about everything else except the D object, then you can. Or if you want to forget about everything except the E object, then you can. That projection works fine. Because what you have is basically pairs D comma E with extra structure.
so
Right.
intuitively, like comma category is like a translation of one category into another category that would be like a universal language.
Right. That's true.
What do you mean by that? Universal.
Well, I mean, like, so when if objects are in separate categories, you can't compare them, right? Like, so they're just non-comparable. But so what you do is with the comma what the comma category means is like, so you see, like here it says exercise 1.3, Roman numeral 6. Given functors F from D to C and G from E to C. So D and E aren't really comparable. They're not completely not comparable.
Right.
But when you functor them into C, but you need two functors. So you have two functors that functor them into C. Now C stands for the universal language. And now within C, you could have morphisms between them, you see.
Right.
Which do
Right.
not exist on the other level. So the C becomes like universal language. But if one of them is degenerating, you see, then the whole picture of translation becomes a little bit obscure. So.
Yep, good point.
Yeah, there's a diagram which it would be helpful to see this diagram actually. So the D and E are both pointing into C, and that C that they're both pointing to links them together somehow.
Right.
Right. Right. So you have
And that
separate...
square is taking place, I guess, in C. So, FD and GE, that's all taking place in C. And if it was if it was degenerate, half of it, then it would be a triangle, because you just have like something like that, the identity or something, I guess. I don't.
Right.
So they just show these triangles, and you're wondering, what's that triangle doing? But it would be more easy if it was a square.
Yeah, well, the triangle's collapsing to squares. That's So where does that come in? Oh, yeah, that comes in with limits.
Square collapsing to triangle, I think, yeah.
Sorry, yes, square collapsing in triangle because one side of the square is the identity, is an identity morphism. That's why.
Right.
And how does that relate to limits? That'd be interesting to.
Oh,
hear.
limits. Yeah. So can you still read this? It's smaller.
Yeah.
Limits. So when you define limits, you're basically talking about triangles all the time, right? So when you have a cone, for example, a cone requires the legs of the cone, all of the relevant triangles involving those legs have to commute. And then when you have morphisms between two cones, then these upside down triangles all have to commute. But you can also look at them as degenerate squares, which in fact she does, because you can look at a cone as a natural transformation from a constant functor to your diagram functor.
Mhm.
Hmm.
She says here the constant natural transformation, right? Like that's the up above the constant.
Let's see. Well, a morphism gets mapped to the constant natural
Okay.
transformation. Yes.
Which is the identity, basically, right? Is that
Yes. Yeah. Well, it's value. Yeah. So a natural transformation is, is a whole bunch of separate
Right.
things, right? But every one of those is
the identity on functors?
the identity. Yes. Yeah. Basically. So the way she defines a cone is as a natural transformation from one of these constant functors to your diagram functor. And it's true, it is a natural transformation. Natural transformations are all about commutative squares, right?
Right.
But in this
But these
case,
are triangles.
right, but there's a constant functor, which means that one side of the square gets collapsed because
Right.
it's just identity, morphism, and that means that everything is triangles. But she does use this language, which is actually new to me, of describing a cone as with the natural transformation double arrow. And that's all over this proof.
Yeah.
So it is important to understand that.
You know, I really wish they would have used a slight notation over the C when you think of it as a constant functor. But anyways,
Hmm.
Yes, I would. Yeah, something
Hey.
delta sub C, I think would be the way to go with that, because it is. It's also called the diagonal
right,
functor, like the diagonal
Mhm.
functor at the object C.
right.
But
The diagonal functors where you basically plug
actually
in
she does.
copies. Is that right?
She does call it the delta right here.
Oh,
Sends an object C to the constant functor at C. So
Yeah,
it's plugging in copies into the shape. Is that right?
yes, exactly. So you get a single object and you just
Oh, and a single
everywhere
object, you repeat the object.
So you're given,
Right.
yes, you're given an object C, and everywhere you need an object, you stick that one in, and everywhere you need a morphism, you stick the identity of C.
mhm.
And that gives you a perfectly, it's a trivially commuting diagram. It's fine. Anyway.
Okay.
let's see.
Thank you.
What else? Yeah, so I got up to about this point here, which shows that, let's see. So they want to show that this formula is defining an actual functor, and that will be the left con extension, or a left con extension. But they're
The
only
arrow part of it, the functor part of it, from D to E.
yes. Oh yes, sorry, yes. And that's true. We need more because in order to have even the right type, in order to even having a candidate for a con extension, you need to supply not only a functor here, but the natural transformation eta to complete the.
Right. You
Triangle.
actually have to also give it the universal property, but. which
Yes,
I
well,
think
yeah,
is
that's
what
that's
the
just to
part
get
you're
the
getting.
candidate, right? Once you have a candidate, if it has the right type, then you can argue that it has the properties that it needs to in order to be a left Kohn extension. So yes, that would you have to also show that it's universal. Anyway, it takes a while to get there. But this, on the face of it, is just an object in E.
Right.
Because if you have this functor here, then and its colimit exists, then the colimit in particular gives you a, she calls it a nadir, like the vertex of the
Yeah,
cone.
I've heard it called a co-apex or something.
Yeah, oh, that's good too. Right, and when we talked about limits and colimits previously, we always talked about cones and cocones. The difference being that the arrows come out of the vertex of a cone, but they go into the vertex of a cocone.
Right.
But she's instead using the terms cone over and cone under, with the idea that the arrows are always going down on your page.
I see.
Mhm.
Yeah. Anyway, so I had to adjust my thinking a little bit to that.
So just
Because
very
often they'll
rough,
call it a
just-
cocone if it's going down, like for the co-limit, it's a cocone.
Yeah,
just-
I like the term cocone too. Sorry, go ahead. Andres.
sorry, this under, so just very roughly, and I didn't read everything, but what the, the K down little d is about morphisms in the category of D. And I guess with the K coming from C, I guess, right? And
Right.
and so what the projection does, it's almost like inverting it partially to get back to C, and then you go from C
Exactly.
to E. So the idea is that if I want to extend, if I have something that works from C to E, and I have this kind of inclusion of C in D, and D is broader somehow, then in order to make the extension work for D, I have to kind of invert back from D
Mm,
and then use the regular thing. So it's like I have to find the best thing in, well, I have to find a limit of things in C that will go to E. And kind of like, so it's kind of like taking a limit of the inversion and then applying the normal thing to that.
Yes. I mean, she calls it an approximation, right?
Sure.
So
But an
C-
approximation in the sense that like the reals can approximate the
the
rational.
rationals approximate reals,
Rationals
yeah,
approximate the real. So
right.
you work back to find like what is the best, but it's a limit of approximate. I mean, so she's saying it's an approximate answer, the best approximation. But in practice, what it means is like if you took, if you wanted to know what the value should be on the reals, you would look at the relation of that real to maybe a bunch of other things and see how that could be related to rational numbers, and then get a limit on the rational numbers, and that limit would be your answer or co-limit or whatever,
Right.
something
I-
like that, right?
No, I think that's exactly it.
Okay.
There's
Yeah.
an example following this theorem, which
Can we look at
actually
that?
does that. Yeah. That was
Yeah, I was
really
actually
helpful for
looking
me.
forward to
Just
this
hanging
example.
in there, I just.
Example,
could
yeah,
somebody
627.
So why is it that the co-limit is the intuition? Why do you, right?
Why would
He
you?
says,
why would
oh,
you-
it's natural to consider the co-limit of this.
Yeah,
thing.
okay, so before we get to the reals then, yeah, I didn't get a whole lot out of this
Introductory section.
intuitive introduction here. But yeah, that does make sense. So we should consider all possible approximation, so if we look at things in D, we don't have any way to map them to E, but we do have ways to map things in C to E, right?
Right.
Right.
And we can look at the relationship of things in C to D. So we can say, all right, so what are all the things that kind of relate to my object little d in D that come from C? Okay, so that kind of makes sense. for
So,
where you
so,
get the
so you
K
want to
down.
kind of work backwards, but you have to do it on a higher level. So you work with cones. It's like you're working with these complicated structures and saying like, what would happen to this complicated structure if then I work back and So you have to do both. You have to kind of you have to invert back, but you can't just simplify it. So you have to say, well, we have this richer structure that the cone gives us or the co-cone gives us. And then you use C to E on the whole cone, and you'll get some kind of limiting structure, something like that.
Yeah, well, there will be, I think that's about right. There'll be many possible approximations in C of your object in D, and we want to somehow sort of summarize them, like to pick the best, or to pick a sort of representation of the best, or all those approximations at once.
Well, kind of like a real number
Kind of what
is
limits do.
a real number is an equivalence class for all kinds of limiting sequences of rational numbers,
Yeah,
So there's this vast amount of things that it can be related to, and it's an equivalence class. But then, so for each of those, you would go back and get the what would be happening to each of those sequences, and when you go from C to E.
Mhm.
yeah. No, I do want to do that example. I've been looking forward to it, but I guess perhaps
And also
guidedly,
to
I was
say,
trying to
there's
read the first.
she's very clear, but I don't know how many people have been watching the Richard Southwell video on Con extensions. It's like 5 hours long. He just has a wonderful aura, and he's kind of pokey, just goes on and on. But he's very, he's at least understandable on a different level. I mean, it requires a huge amount of patience. But I think the gist of what he's doing, I'm only a couple hours into it, but he's looking at this type of adjoint functor relationship. So that what I think it was Wei Ning was showing, where you have when you're talking about limits or co-limits, you have a category and you're mapping it into the C to the J, right? Like the maps into the category, so into these shapes, right? So when you do that, that would be a functor, and it has two adjoints. It has a left adjoint and a right adjoint. And the left adjoint, basically, I think, so one of them is like the co-limits and one is like the limits. And so that's a classic example of Con extension would be. So with a Con extension, you'll have a functor going one way, and then if you want to go back, you look at its left adjoint, or you could look at its right adjoint. So they kind of get extended either way going backward. They're inverted either way. So that's the example to try to learn and think about, I think.
Yeah, I think she's not yet defined adjunctions here, but
She defined adjunctions in chapter 4. They're like a building block.
Yeah, okay, it's coming up soon, but there's a trivial functor from C to the diagrams in C of shape J.
And so exactly, and all
Trivial
these,
functor here.
all
So
these,
whenever you have a trivial, whenever you have a
please.
trivial functor, you can ask, does it have a left adjoint? Does it have a right adjoint?
Yeah, exactly.
And in this case, it may well, and one is the limit and the other is the co-limit. So go ahead.
Just to finish my thought, so philosophically, and that's one reason I'm studying, it's adjoint functors all have to do with what you said, like the triviality. So if you want to classify what are trivial things you can do, you see, so adjoint functors are, you'll have a trivial functor and then you can invert it going one way or the other way. So it's interesting to try to classify that.
Yeah. The fact that many interesting constructions are the adjoint of a forgetful functor, right? So the free constructions.
Yeah, so one thing about this was that pi functor really is kind of like a forgetful thing. It's really just picking out the C components and of the things and forgetting all about the morphisms to D, which seem like the important part. And then you compose, you compose it with F, and so then you can sort of, it ends up giving you things in E that are images of things in C. But I think, and I was kind of wondering, well, whatever happened to those morphisms? The comma category also has, those morphisms from KC to D. And now we've used this forgetful functor to just throws them all away, and then we compose it with F, and that doesn't add them back or anything.
I kind of feel that
Where are
the
they being
forgetful-
used?
the so-called forgetful or projection function here really doesn't really mean you forget things. It's just saying that, okay, for now, you just say, okay, we just care about the objects in C, but still the morphism in the comma category still define the diagram, the base of the comma. So basically you are still not forgetting the information. It's just the operation wise, yes, we are forgetting about the morphism for now, but I think
Right.
the morphism still defines your diagram.
That's true.
Your index
Yeah, they're
diagram.
still in that category, and they still do enter into.
Well, I
the
don't
group.
know that they go into the diagram. I mean, the diagram really is just, objects, are of the form f of C, and
The-
then, and then the, lifting F in there. I think
Oh,
what
you're
it has to
saying-
do is
You're
the
saying that the
cone
morphism
itself,
in D,
the cone has to be a function from the comma category down to the apex. So every leg coming down has to relate back to, an object in the comma category, which does include all those morphisms.
okay, I
So I
see your
think it's
point.
the
yes.
legs that end up with all the morphism stuff.
Yeah, I see your point. Yes, the base of a diagram, the morphism is actually all the morphism between the C objects that we choose from the comma category. That's what you're trying to say. It's not the morphism that is from KC to D.
Right.
That I agree.
As
I
far
think
as the
you're right.
diagram's concerned, we've kind of thrown away the morphism part, and we
Yeah.
just care about the C part,
Yes.
mapped by F. But the cone part or the
Mm-hmm.
co-cone part, I think there's a leg. There has to be a leg for every object in the comma category.
Yeah.
But even the projection though, it pulls out the C object, but the arrows, it's a functor. So the arrows from the comma category to another object, the morphism has to come C to C prime, right? So the arrows still get mapped to C. So you don't throw away the arrows. You just project
Well-
it both down to the object and the arrows in C. That's my understanding.
Well, I think so the pi guy it's mapping,
Yes.
it's taking just the C component of the things in the comma category to map the objects, and then
Yes.
to map morphisms.
The arrows.
It
yes.
only cares about the part between C and C prime, the G between
Correct.
C and C prime. And that's what
Correct.
it lifts back into C, and it's throwing away it doesn't care about the morphism
Deco-
part
I mean,
between,
But-
It's helpful what, I find it very helpful what Wei Ning was saying, but I think what it means is that like, K is taking us from C to D. Then we
Right.
look at the comma category, and then we project from the comma category. So what that does, it kind of gets us back to the object C, but I think like what Wei Ning was saying was that, but we have the arrows between like a C and a C prime and a C double prime and all kinds of things. But so when we go back, what's the difference? And I think the difference is that
Okay.
we're filtering out, you see, because
Yeah,
when
there's that too.
when the functor mapped from category C to D, it could have made things degenerate. It could have, it could have collapsed things, or it could have done different, things. So when we go back, but we retain, we will only get certain morphisms between C and
Yes.
C prime and C double prime.
That's
And certain
true.
morphisms will
That's
just
true.
be lost, that are in C.
Yes.
So it's kind of like filtering out and selecting the ones that are relevant.
Yes.
Ah,
That's a
right.
Yes,
very
We're
good
not
point.
getting all of C. We're getting, right, you're saying like a
The ones that could
subset
go back and
of
forth.
C and
Right.
Right away
various
with that.
arrows between them, and it's only and then it's F applied to that image that gets,
It's kind of distilling the stuff that's relevant. It's distilling the relations in C that are relevant for the stuff in D that we want to extend on. And
Yes,
Yeah.
that's a very good point. It's
Yeah, I
only
agree.
it's only the C's in capital C that have an arrow into the D object, right? So
Right.
anything that does not have an arrow into the D object are ignored. So that's
That
a
is-
good point.
That is
Yeah.
correct. And then I want to say, just as you guys probably have mentioned earlier, that in the morphism in the comma category, actually is preserved by the projection functor back to C. If you have a C to C prime, C prime
Right.
in C, actually you have a morphism in the comma category as well.
Right.
And then it's actually preserved. It's a commuting
Wait, say
triangle.
that
But if you
Okay.
think about comma category, the objects are KC to D, and then you have another KC prime to D, because they are pointing to the same D, and then you have a C to C prime.
Mhm.
Then would be the same. There will be a morphism in the comma category as well. You will form a commuting triangle.
Right.
And so that was for the
Well,
particular
right, I think that's a
object
selection
D,
criteria,
like
though.
that it's
Yeah.
all revolving around in the particular object D, and then for each D you'll get a different basically setup.
Yeah.
Right.
Mhm. Right.
Like if D is the initial object, then there's no arrows into it other than from itself, right? So
Mhm.
there may or may not be a projection back to C. We don't know if there's an element in C such that KC is equal to D if D is the initial object. There may or may not be one. So
Right.
that's an example where we don't know. I mean, where it might not even map back.
Mhm.
So I was just, trying to get it. It just seemed like, we invent this whole comma category and then we throw, and then it seemed like we're kind of throwing away all the interesting stuff to create the diagram. And yes, we actually did do that, but then it comes back in the cone, I think. So when the co-limit, if you say the co-limit exists, then it's giving you this cone that has all this structure, and that structure is partially driven by the comma category. So you know that for every object in the comma category, there's going to be a leg going down. And so that's a fairly rich structure that the co-limit is giving you.
And then maybe what's key for these constructions in these cones is that the whole universality will be based on that. So that's why we have to work with cones, because we want this stuff to be universal. And this is where the universality will come in, I think, when you get the limits and the co-limits.
Right. I think the universality of the cones helps give you that LAN KF of G that's kind of right at the base of that diagram there. Because you got to say, we've told you what the functor does on objects. Now we have to tell you what it does on arrows. And this is, you're using the universal property of the co-limit to get that.
Yeah, what I wanted to
Mhm.
point out was that the arrows into objects in D, the arrows into little d, do show up as what she calls indexes on these legs here, right? It's the subscripts there are arrows into D, arrows into D prime. And particularly, you look at the way G is acting on those arrows, right? So if this one corresponds to some morphism F between KC and D, and then here you have a morphism from KC to D prime, is F followed by G. So they do, you do need those things eventually.
Right. So you get basically two cones going into the same thing and then use the universal property to say, oh, there has to be this unique thing that goes between them.
But I do agree with Peter that in the intuitive discussion at the beginning, where she says, okay, I guess I buy the stuff about approximations from the left.
Mhm.
But then when she says it's reasonable to define this to be the co-limit of the diagram,
Why?
that did not strike me as reasonable immediately. I'm like, what?
Well,
But
okay,
Isn't
that's
a co-
maybe that's where we can look at that example. Because if you think of a co-limit as approximating from the left, in other words, all the C's that map into this, approximating D, then when you take the co-limit, then it's the closest you're going to get. So that's why.
you want the best, or you want
Well-
you want to distill all of those approximations into sort of an ideal.
Exactly. Right.
Well, or another way to say that, that's the universality. So like in the Kohn extension
Yes.
diagram, where that Kohn extension will be better than anything comparable that could fit there.
Right.
That-
Right.
Yeah. Or
But
if
yeah,
you
I
look at
think,
sorry, go ahead. I was just going to say, if you look at all these cones with the same diagram at the base, it's a family of cones, or if you say it's a cone category, and then the co-limit is actually the initial object, it's actually the best one.
Yep.
I think that's what the intuition is trying to say. Yeah.
Right.
Yeah. But yeah, Yang Yao was suggesting a concrete example, which I think is a good idea.
Okay.
Let me pause and read this.
I mean, the key to understanding
Wow.
a post set as a category is that there is an arrow from A into B if A is less than equal to B. Right? So
And A and B are in Q in this case, is that right?
right, or in R, the non-negative reals. So either way, it's made into a trivial category where less than equal to is the arrow.
Mhm.
So there's an arrow between 1 and 2, there's an arrow between 1 and 1, because 1 is less than equal to 1, and so on. And then the limit is the infima, which is the, if you have a set of numbers, then you take the infima, and that's the limit. And the co-limit is the suprema, which is the biggest. But of course, right, Q is not complete, so you don't have limits in Q, but R is complete. So yeah, R has limits and co-limits.
Yeah, or has limits and co-limits. Your subsets have to be bounded, right?
Yes,
The set 1, 2, 3, 4, 5 doesn't have a limit in R.
Right.
It has
Right.
to be restricted somewhat.
right.
Yeah, I was going to try to draw.
So
Not drawing.
what are these terms? Infima and suprema?
Maximum,
mean?
okay, infima is the minimum, and suprema
Okay.
is the maximum. It's just that the
Of
word,
these bounded subsets. Okay, using whatever your thing. Okay.
right, right. It's just that the word max and min are not used because it does not necessarily exist by itself, but the limits of them are. That's why it's called infima and suprema in analysis.
Hmm.
Like all the rational numbers that are less than the square root of 2, for example, right? The suprema of that,
like 1.4, 1.41, 1.414,
Exactly.
1.5.
Right.
I say.
Those are all rational numbers, and you sort of imagine them as dots going up to this one point that you can sort of feel is there, but it's not really there because it's not a rational number.
Never gets there.
Right. But if you take the supremum of those things in real numbers, then you would get square root of 2. That makes sense.
Okay.
right? Well, but of course, in mathematical analysis, you define the reals as the equivalence class of sets of rationals. So, it's kind of circular. But anyways, so that you can have this limit and co-limit exist. But anyway, that's beside the point
In
here.
that, I'm just curious, in that where you're showing the arrow, it goes from E to the D and E to the C, and they have a K star there, right? And I'm trying to understand the K star, which is like the adjoint of the left can extension and the adjoint of the right can extension, right there. You see it
Oh,
says
this one.
I
K
think-
star, yeah.
Yeah,
And I
isn't
think,
it like composition with K?
Yes.
Oh, yeah.
It's a precomposition
Precomposition?
functor. Yeah.
Yeah.
It's induced by the morphism.
Here.
Yeah.
So there's a
Precomposition
precomposition
functor.
functor. I actually had to take a sidebar for
okay.
3 minutes to convince myself that that actually is a functor, but I now believe that it is. You have to go and check. But yeah, K by precomposition does give you a functor from functors from D to E to functors from C to E. And
Oh, I
yeah,
see. Okay, so K takes us from C to D, and if I have something from D to E, I just precompose by K, and I'll get something from C to E. So that's
Right.
another example of a trivial functor, right? That's just
Yes.
trivial to do it. And so these two are the adjoints of that trivial,
Right.
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 Um,
Mhm.
I have
But the trivialness,
that's
so precomposition is trivial, but what's not trivial is these spaces E to the D and E to the C, because those are functor categories, right? Like, so those are kind of complicated. I mean, those are hard for me to think about.
Mhm.
Yeah.
Because that's going a level above. So instead of just talking about C, D, E, now we have E to the D and E to the C, right? And so
Yes.
and so that's another way of saying that's another way of saying, like, if you want to go back, if you want to make this extension from C to D, you need to be able to take what you have in D, go back to C and apply that, but you need to do it at a more complicated level. And so this E to the D is a more E to the C, that's the more complicated level where things like cones and co-cones, I guess, make sense or whatever. More
Yeah, so it's
complicated
kind of
creatures.
interesting what you're saying, that these functor categories are pretty complex things, but sort of by just moving up to a different level, well, okay, they're just categories and we don't really have to think about them that much. And now we have this trivial functor K star that just kind of goes between them, and it's like you say, it's pretty trivial. And now we can think about having left and right can extensions. But then when we think about what that actually means, and then it gets complicated again.
Well, I think it's the power of a junction. So you can have and you always have to have something trivial in a junction. So precomposition is trivial, but in this very this is like a meta context.
Right.
So in this meta context, it has the left adjoint and the right adjoint that'll be highly non-trivial and with the junction, basically what you have the same information, but in a different context. So,
right.
So it's like you're synchronizing, information between different worlds. And so precomposition has loads of information in it. And that same loads of information will be in these other synchronized versions, but they'll just be very, they'll be bizarrely complex. But it's the same information.
Right.
But the context is different.
Right. Yeah, it's interesting that if the left and the right Kohn extensions exist, then they are the left and the right adjoints. So interesting.
I think Wei Ning had a question.
Oh, I was just going to ask you guys about the example that you were showing earlier in the section 6.2 about the projection of the rational into the real, non-negative real. The last line, there's the exercise, point in the exercise saying that 6.2.2 explore when to the left and right extension coincide.
Hmm.
I haven't figured this out yet. I just wonder if anybody figured it out.
I didn't get anywhere near this.
Okay.
But I think it does make a lot of sense to skip forward and look for examples and skip forward and do exercises, particularly if you're getting stuck with the, like trying to read the general proof. I did find that helpful in section.
I actually feel this proof in this section is actually quite well clear and well written. It kind of like going through steps, and I can kind of understand what it's trying to say. But the examples, I can only understand probably the first one, and I start to feel that gets more complicated for me. Maybe it's because I lack some of the context they try to talk about in the examples.
Oh, wow. Whoa, that's a big old diagram.
Yeah.
Okay, I'm not going to look at that right now. I'll try it again later. Yeah.
Yeah, but the first one is a good example. I think it's something that at least I think I can relate to. Yeah.
First, it has all limits of bounded subsets. 6 to, oh, okay. So it's actually, you can't apply 6 to 6 because D is the reals, non-negative reals. And that is not locally small because you could have these unbounded sets which don't have limits. So we're not applying.
No.
Actually, I think that's E.
No,
right?
that's
The
still
negative
small.
Is that locally? Oh, I'm sorry. Sorry, it is locally small. Of course, yes. Locally, they're actually extremely locally small because all the Hom
There's
sets
only
one.
one of them.
are of 0 things or 1 thing. No. I was confused. But the co-completeness we do not have. It's not. The reals are not complete with respect to any diagram. You can't take the in for the soup of any set. It's only the bounded subsets. And so we're not applying, I think we're not applying corollary 6 to 6 directly, but we can apply 6 to 1.
Right.
The sort of lead up to that. Let's see, we have to, for every D and D, the co-limit of this thing exists. Okay. And I guess why does the co-limit exist for that case? That must bound things. I guess for every, well, now I'm confused. For every rational number, D is, what are C, D, and E here?
What is the comma category? in this example?
Just for clarity, I missed parts, but infimum and supremum mean least upper bound and greatest lower bound, right?
Yes.
So that's different than
Yes.
just maximum and minimum, right? That's
That's right. In finite cases, they are the same, but in infinite cases, like rationals, they're not the same.
So I think in this example, you were curious about what is C, D, and E categories. C, I think, is the Q, the poset, and then E is the non-negative real poset, and D is the real number. So you see the left hand extension is from Q to R, right? Or did I misunderstand?
Q from R. No, I think that's exactly right.
Okay,
Let me actually, let me try to make a diagram here, if I may.
yeah.
Try and share my whole screen. Desktop one, let's try that. Screen. Okay, so rationals. All right, let me see if this works. Rotate. Oh, we're green again for some reason. All right, so we have Q. All right, Q.
Or is
Yeah.
QD?
And then R. Yes, that's right. No, well, they both are. No, they aren't. Because D, we need to be the real numbers. so that this inclusion will be interesting.
Oh, I see. Left conic extension along that. Okay.
And let's see, this is like R,
Yeah, non-negative R.
right. I need to move your faces out of the way. Yeah, so she actually positive R apparently. Yeah, like that. Okay, so this is our C, D, and E.
Okay.
Okay, well, that's crude, but does that look right?
Looks good.
Mhm. So we have this function already. So if we know how to take any rational power of 2, then we want to start taking real powers of 2. And that's what the extension part of it is.
Mm-hmm.
Do that with the.
So would it make sense to tell me what the comma category would be in this case?
Ooh, absolutely. So suppose we have, I guess I'll call it little d, which is a real number. Okay, wait. So we're given k, which is just the inclusion, and we're given f, which is the exponentiation for rational numbers. Okay, so what would k down arrow d be? Sorry?
I was just going to say the comma category means that everything that is less than D in R, that would be your collection of
Is that right? So it's
object is C, right? Because your morphism is less than equal. Is that the case?
It's the set of all little q and arrows from
Right, D. Mhm.
Or you could use the less than or equal, right? Like so.
Yeah. Your arrow is less
Because
than
K,
equal.
K is just inclusion, right?
Yes.
Yeah.
K is inclusion of Q into R.
Yeah.
So it's just Q.
Yeah,
D.
it's just Q.
Mhm.
So you're
And so
saying it's.
you can write that down, but then you can rewrite it. You can write it down further. That's Q is less than or equal to D. Yeah.
yeah,
Right. All Q less than equal to D.
yeah. I like it.
Okay.
So that is precise. So if again d, which is a real number, was a difficult real number, an irrational one like the square root of 2, you can approximate it with the collection of all rationals which are to the left of it.
Well, but I mean, and to emphasize that it's the relations also, so that that relation could exist or not, but it's less than or equal, so it exists. So the element isn't just the Q, but it's also that that
Yeah.
arrow.
Well, the fact that
It's the
Q has
Qs
to
that are
have
less
that
than or
arrow,
equal to D.
yeah, the
Right.
fact that Q has to have that arrow is a witness to the fact that Q is on the right side, or sorry,
Right.
is on the correct side, which is on the
Left
left.
side.
Q is less than or equal to D. Yes. So yes. So 1.4, 1.41. The arrow from 1.41 to square root of 2 is a nice example.
So then the functor F is that exponentiation. So the things we're getting in R greater than 0 are the Qs are 2 to the q.
Right. Exactly.
And then the limit of all those, or the co-limit, how does that work?
This is confusing because limit has a meaning in real analysis and it has a meaning in category theory. And I think they're turning out to be
Right.
exactly the same here.
Right.
Wouldn't that be nice?
Yeah.
Okay, so in
It
this
does happen
example,
sometimes. Sorry, go ahead.
so K down arrow D is represented as all Q such that Q is less than or equal to D.
Right,
So then the projection of that into C gives you all the rationals that are less than equal to D, right?
right.
For any D in R.
Well, yeah. I mean, usually we're fixing D at this point, and then
Yes, we're
Right.
fixing D. Then you take the limit, which in this case is the suprema. The co-limit is the suprema. And
well,
what
first
is
you
the
have to map into R. You did, I don't know if you did that.
well, no, we're talking about the
Now
okay,
we're going
this- we're ta-
backwards. So D is in
We're
R,
take-
square root of 2 is in R, but we need to be able to raise it to the power of whatever.
Q.
right.
Power of
But
2.
that
So
so we're
then,
taking 622. We're taking the co-limit of this functor,
Mhm.
which takes the set of R, the Qs, into R, I mean into E, right? And
Right,
those are all the functions that map that to the 2 to the qth power. And we're taking
Right.
all Q that are less than or equal to D.
right,
And then we're taking the co-limit of that, which is the upper bound, right? The supremum of all the 2 to the 1.41, and I mean, sorry. Yeah. So we're taking the supremum of a set of rationals, and we're saying that is the co-limit. And that we're saying is the value of the extension.
The supreme of the rationals raised to the power 2. or
Right,
Whatever, yeah.
right.
Yeah.
So we're defining the supremum of that to be 2 to the D, where D is the real.
okay.
Yeah, that's nice. And the supremum, so what is a supremum? Well, it has to be at least as large as anything that's in the set, but also it has to be
Right.
not too large.
That's right.
Right.
It's the
So, like-
smallest that satisfies that condition.
Smallest thing that satisfies that condition, and that is a universal property. It's the same as the universal property that we use to describe the co-limit.
Exactly.
So like 3 would be
Huh.
too big. 3 is way too big. 3 works. It is a candidate for the co-limit, but it's not the best candidate. The best candidate is square root of 2. I'm sorry, I'm a little babbling, but yes. So that's exactly, it is the same thing going on there.
So that's, so to read it now, like, so K down D basically means that all the things that K has sent that will be less than or equal to square root of 2, it's just kind of selecting the criteria that, let's say, what are things that are less than or equal to square root of 2 that are rational? And then
Yes.
the projection says, well, okay, send them back to the rationals, those that came from the rationals, send them back, but we've selected, we've filtered out, we've selected the ones that are less than or equal to square root of 2. And then
Yes.
once you've sent them back, then raise them to the
Then
power
raise
2.
them.
And then when you have all these possible candidates, then you take the co-limit. And so the co-limit will be the supremum of all those things raised, all the rational numbers raised to the power 2 that had been filtered out.
Yes.
And so you get a
Yes.
limit. It's kind of like you reversed it, and then you reversed to get all the candidates, and then you did everything to those candidates, and then you took the limit among the outcomes.
Right.
Yeah, sounds right. No, that's very nice. I'm going to step out for just a moment. I'll be right back.
This was very helpful to try to learn a little bit about something. This was very dense and not clear. So I really appreciate it. And I'll be back in 2 weeks. Are we meeting in 2 weeks, right? Is the
Yes,
next meeting?
presume.
I
Okay,
think
I have
so.
to
We
leave
haven't-
now for Eurovision. I'm staying with my parents, but goodbye.
Okay.
Okay, bye, Andrew.
So let's see. Is 2 to the square root of 2? That's not 2, is it?
No,
No.
definitely
So
not.
the, yeah.
It's bigger than 2.
Right.
The
So what
square
are,
root of 2 is bigger than 1.
so what are the things that we're, when we get the, so when we, what are the things that we're getting in R, that are greater than 0? There are all these approximations getting close to the square root of 2, all raised to the power of 2, or yeah. And that, so why does that give us what we want? I'm missing something.
Okay, so let's see. So when we-
Okay, so the
when we
question is, we want to figure out what is 2 to the power square root of 2. Okay, that's what we want to try and compute. But what we have,
That's what we're trying. Okay, got it.
but what we have is 2 to the rational powers only, right?
I see.
And so how do we approximate 2? How do we get 2 to the power square root of 2 when we only have 2 to the rationals of power? Well, you take all the rationals that are less than square root of 2, and you compute 2 to that, and 2 to the other, and 2 to something.
I see. Okay.
And then you take the limit of that, and that is what we're defining as 2 to the power of square root of 2,
Okay,
right? Yeah,
got it. I just got confused that we picked the square root of 2 as an example, but then it was also 2 to the
I know.
base
Right.
exponent. So if
right.
maybe if
So-
that was square root of 3, then
Right. So Hugh, if you put in like ... and then 2 to the power square root of 2 in your diagram there, yeah.
Yeah, sorry, just a minute.
So it's like 1.41. I don't know what the next digit is, but ... and then 2 to the power square root of 2. Yeah,
Yeah, and
Exactly.
Peter, you're
exactly.
right. The 2s are doing different things here, and the example is
Yeah.
maybe poorly chosen, but pi would have been better. 3.141. Yeah, okay. Anyway, if I did it again, but I'm not gonna draw all this again.
that's fine. That's
Right,
fine.
right.
It's just my confusion. But right.
Right. And so I think,
But
yeah,
in that ... that final number is not one of the ones that we actually generate. That is the limit of all
exactly.
those other ones. Right.
That's right. Yeah. So if you would just draw one more number, draw the square root of 2 on the lower R. Yeah.
Square root of
Yeah,
2 down
there.
here.
Yeah.
Oh, yes,
put it-
because that's
put a-
that's P, right?
Yeah. So that's, yeah. D
That's
is
our
equal
D,
to
yeah.
square root of 2. Mhm.
Excuse me.
Exactly. Yeah.
Okay, and then square root of 2 just kind of emerges magically over here on the right. Oh, sorry.
2
square-
to the square root of 2.
Right.
yeah.
I will fix that.
I mean, this is analysis 101, right? How to extend the power function to the irrationals when you know what it is. Well, you first start with the power function for the non-negative integers, right? We know what that is, right? 2 to the 1, 2 to the 2, 2 to the 3. And then somebody will ask, well, what is it 2 to the negative 1, right? And so that's the first extension, is how do you extend it to the negative integers? And then you play a trick. And then you then say, well, what is it for rational numbers? And then you extend it one more time. And then this is the final extension, is to you have to use limits now. Whereas with the rationals, you didn't have to use limits. You could just do it as an algebra, but as a fraction. But here you have to have a limit.
Yep. And she walks through some of that at the beginning of this chapter, I think.
Yeah.
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 That's why the reals are amazing. The real numbers, the completeness of the real numbers is one of the most fundamental, discovery or attribute that makes reals just the best. Okay. The completeness is such an amazing thing.
It's pretty awesome. And then of course you want to solve all of your polynomial equations. So you have to throw in the square root of -1. You have to throw in I and talk about complex numbers.
Right.
A little bit different.
But that's just algebra. But completeness, the idea of the completeness of the real numbers, that's just, I don't know, it's just so amazing at a fundamental level, I think.
Definitely the biggest step. It's like the hardest part of that whole extension process.
Yeah, yeah.
Cool. 6.2. I'm a little bit curious now, just looking ahead. Wei Ning mentioned there's an exercise on this.
Yeah, I mean, just whenever anybody has a chance, and if you have
interesting.
any insight, I'd love to get a hint and how to.
Give conditions on a functor like this so that the left and right Kohn extensions exist and coincide. Huh.
And coincide.
Because that happens here, right? I get if you try it the other way, it works just as well. The right Kohn extension gives you the same result.
Oh, I see. Because you're just approximating from the other side and then taking the other limit.
Exactly.
Yeah.
Yeah. So I guess one way of approaching the exercise would be to say, okay, well, we did it here, right? It worked here. Now, why did it work? Why exactly were we able to do this? We have to like analyze the steps that we took very carefully.
I think actually Peter might be onto something. You're approximating from the other side. Basically, you're reversing all the directions, and then you just need to know if you come from different directions, they all end up at the same point, and then what the condition is.
Yeah, I'm wondering if like is continuity involved here? Is it like do these functions have to be continuous?
That's my guess, is that it has to be, they have to be continuous in some sense. I mean, even though rationals are not quite as continuous, smooth, but nevertheless, they need to be continuous. Because if you have a jump, then the left Kohn extension comes this way, and then the right connection comes this way, the co-limit and the limit, and then they won't coincide, right? But if they're continuous, then they have to coincide.
Interesting.
I mean, that's sufficient. Whether that's necessary.
Yeah, they don't ask for like exact like if and only if conditions.
Yeah.
They just say some conditions.
But wow. All of this category theory and Kohn extensions to be able to extend the exponential. But the idea, though, is amazing. Though this is mind-boggling to me.
I guess that's where this
extension general
the
category.
title of all concepts for Khan extensions comes from. It's
Yeah.
like, yeah.
But think about it this way: if you understand it, you understand everything. Wouldn't it work there? Yeah.
Say it
Sorry, say
again.
I would say that if you, since this is all concepts are Khan extension, if you understand Khan extension, that means you understand everything. So it's probably worth you put in the effort. Right?
That's right. That's right.
Okay, well, I
Yeah.
would like to finish this proof at some point. Yeah,
Oh
it's
boy.
it's not easy, but the pieces are all there, I think.
Actually, I think the proof is written at least clearly, even though I think you just have to look at it as multiple steps. First, you have to prove the factoriality, and then prove the eta is natural transformation, and then the last step is to prove the universal property of the Khan extension. And if you try
Yeah.
to break it up in this, and then this proof actually is pretty well written, I think.
Right. Yeah. I mean, what's difficult is the notation, right? The fact that you have like subscripts on a subscript. It's
Yeah.
like this is the most complex, diagram with different levels of arrows that I've seen. So
Right.
yeah. I mean, look at that.
You have this thing which has superscripts and a subscript, and the subscript itself has a subscript.
This is try to say the leg of a cone, the lambda something.
Yeah, they're all just legs of cones. It's
yeah.
Right. But and then one is the identity, but she wants to say which identity it is. So, yeah.
Yep. Yeah, this is where programmers can contribute something, I think, in terms of once the notation becomes like this. But anyways.
Yeah, the notation is often like not quite complete or legitimate, like but it's useful. What am I trying to say? So for instance, just writing that, this functor is the left Khan extension. Well, that's really only part of it. You're saying it's this functor, but then you have to give these other pieces too. But it sort of abbreviates it so you could do that. And in many of these cases, like with this pi functor, it really didn't do much. And superscripting it by D didn't change what it did in any way. It just only indicated what the domain was. So, you had pi super D, meaning that it came from the comma category that had D in it. But D didn't actually affect the functionality of the pi guy at all. It's just notationally there in order to indicate what the domain was.
That's right. I mean, it provides the typing, right?
Yeah.
But the pi is defined. Yeah. So from a type language point of view, you need it to clarify the different types of the domain. But the actual content of it, you're right. Yeah. It's just picking out.
So we need a plan for next time.
Ah.
Because I should leave soon.
Yeah, me too. But do more of this, or
that would be my vote. I feel like I can get more out of this, like understand this proof better and maybe do that exercise. Yeah.
I certainly learned a lot today. I mean, by myself, it was hard going, but the discussion we had has clarified a lot. So I feel like I'm getting there. So I wouldn't mind spending at least one more session on this, unless some people have other things.
Well, that's the thing. I'm not sure we have anything else.
I mean, I think this is sufficiently rich that it's worth doing this. I mean, there's also section 6.3, right? The point-wise. And I'm not sure what that is, but
Yeah, I think once she's finished telling us what con extensions are, I think she's going to say, well, actually, those general ones are not that useful. And what we really need is point-wise con extensions.
That is what it seems like she's doing.
It's like, what? Why did I do all that work? If that wasn't what I wanted. Anyway, but we also
And
have
then in section 4, she says it's, they'll be particularly poorly behaved in the case of drive functors. But
yeah, that I'd like to get to that point too. I mean, definitely I'd like to continue the rest of this chapter if other people are interested.
I'm interested. We have one alternative proposal, I guess, which is Antonio's paper on actual applications of con functors in data science.
Yeah.
oh, right.
If people, for example, are really tired of trying to prove extremely abstract stuff, we could jump over to that. I think I would want to keep on chugging on section 6.2, but yeah, open to other suggestions, as Daniel said.
Right. The consensus seems to be to keep going with 6.2.
Is that okay with everybody?
Yeah.
Sure.
Sure.
All right then. And 2 weeks from today is fine with everyone, I gather.
Is what?
Is
Oh, yeah.
okay.
20th. Yeah.
Looks
Okay.
It's Memorial Day weekend, but I don't, in
Ah.
case anybody cares. But No.
I just want to ask something. One final question. Hugh, are you writing still with your finger all these diagrams?
No, I'm
Ah.
well, yes, roughly. So I am using the annotation feature of Zoom. So there's a Zoom annotate button, which is probably showing up there, and I'm using the trackpad on my laptop to actually do the drawing, and that's why it looks so rough. If I had a nice
And you-
setup with a stylus and a tablet, then it would probably
Yeah.
look a little nicer. But
so you
No,
are
it-
using your finger on the tablet
on the trackpad of the laptop.
the
and the track.
Yeah,
Yeah.
it's not great job. This was really
Yeah, it's slow, but it is readable ultimately.
yes, yeah.
All right. Well,
Thank you, everybody. It's
Oh,
also
we'll
very
do it
helpful
in
for
2
me.
weeks.
So
All right.
until
Thank
next
you.
time.
Well,
Bye bye.
ciao.
Bye bye.
All right,
Hey,
see
take
you
care.
guys.